is the nuclear model of the atom. And for the most part, we still abide by the nuclear model of the atom. The nuclear model of the atom says that there is a nucleus. That nucleus is a positively charged center. It contains nearly all of the mass of the atom itself. And while it contains nearly all of the mass, it contains nearly none of the volume. 1/10,000th of the volume of the atom is contained in that nucleus, which means the other 9,999 10,000ths are all represented by those electrons that are surrounding that nucleus. Inside that nucleus, we have two particles. We have the proton, which is positively charged, and we have the neutron, which is neutral in charge. And just to give you a little bit of an idea of perspective, this is a representation of the gold atoms that would have been found in the gold foil experiment. And you can see that little tiny dot here in the middle of that atom, that is your nucleus. All of this that is surrounding it those are all contained by the electrons in the electron cloud. So a lot going on with respect to that. Inside of that nucleus, the nuclear size for an atom of gold is 1/100th of a picometer. That would be about 10 femtometers. So again, I said that we were going to mention those terms very sparingly. This is one of the applications where we would mention pico and femto because of the size. The overall radius, or excuse me, the overall diameter of the atom, we can see the overall diameter is about 288 picometers, of which 1/100th of that diameter, 1/100th of a picometer. So again, somewhere on the order in this case of about 1/28,000th of the diameter belongs to that nucleus. Some things that we can express about atoms themselves. First of all, we express masses of atoms in terms of what are called atomic mass units. Atomic mass units are defined values. Since they are defined, we can talk about them in terms of relativity. There's some sort of definition that we use, and everything else is relative to that definition. And the relative definition that we're talking about here is carbon-12. An atom of carbon-12 is a perfect 6. 6 protons, 6 neutrons, 6 electrons. 6, 6, and 6. And by definition, it is said to weigh exactly 12 atomic mass units, or 12 daltons. Off of this value, we compare every single other atomic mass, regardless of isotope, regardless of anything else. They're all based upon this one value. So, I made mention about a week ago that one of the things that really kind of blew my mind when I first started really getting into science is the idea that everything's based upon a commonly accepted definition of something. And this is no different. We made up an entire mass system based upon the mass of a single isotope, carbon-12. Everything else is measured relative to that. So how do we use this information? Well, for one, we can start to investigate the subatomic particles a little bit more closely. You can see that there are some standard definitions and ways that we can express the quantities and the values for protons, neutrons, and electrons. So for example, this kind of symbology that is being shown here, this is very common in nuclear chemistry. What we have in this symbology is a top number, a bottom number, and a symbol. The top number, as you should know from your post-lecture, is the mass number, which is the number of protons plus the number of neutrons. So if I'm looking at a single neutron, obviously it just has a mass number of 1. It is 1 neutron with no protons. The bottom number here represents something called the atomic number. And we can kind of broadly think of this as the number of protons when we get to electrons, we can also see this kind of represented as charge instead of the number of protons. It kind of varies by what we're looking at. Ordinarily, what we will see is charge is usually represented in this area to the top left, or excuse me, the top right. For subatomic particles, charge is implied because they all have either a positive 1 or a negative 1 or 0. But if we were looking at elemental symbols, charge is usually where we would find in that top right corner to tell us what is the difference between the number of protons and the number of electrons in that substance. If we walk on through this, we can see that from a standpoint of status, our masses of protons and neutrons are relatively close to each other. Neutrons are just slightly more massive. Both are way more massive, almost 2,000 times more massive than an electron is. But what we'll also see is that more often than not, we will talk about mass in relative terms. So instead of talking about strict numbers of AMUs when we talk about isotopes, we'll talk about them in terms of mass number. And in mass number, proton and neutron, because they are practically the same, are given the same value of 1. An electron, which is so tiny by comparison, has a mass of 0. On the flip side, same kind of idea with charge. We know from the Thomson and Millikan experiments what the charge of an electron and therefore what the charge of a proton are in coulombs. However, these values on the macro scale are so tiny, it's virtually impossible to keep track of them. So once again, we're going to go to relative numbers to quantify that. A proton has a positive 1 charge, an electron has a negative 1 charge. Their masses all can fit into idea there. And the ratio that what we will see here, there is a conversion between mass in AMUs and mass in grams and kilograms. Essentially, the ratio is like this. See if I can draw it. 6.022 times 10 to the 23rd AMUs is equal to 1 gram. If you're familiar at all with this number here on the left, should be something that you recognize. This is Avogadro's number. We're going to talk a lot more about Avogadro's number middle of next week. But the idea here is, again, pretty essentially the same. A Dalton is 1 Avogadro's number of a grain. And so what this will ultimately allow us to do is, once we get to talking about moles, is there is a relationship between the mass in AMUs and the mass in grams if I have a mole of a substance. And that will ultimately allow us to use these atomic masses as molar masses when we get to that point. Let's talk a little bit more about isotopes. So with isotopes, what we see is that based upon some other experimentation going on at the time, we can look and see that what we thought might be a uniform beam of ions actually splits in an electric and magnetic field to give us 2 different beams based upon the interaction of each of those with their respective fields. Now, why does this take place? Well, it's because even though they are the same, even though they have the same amount of charge, one of those charges, one of those sets of atoms, does weigh a little bit more than the other. And so it's not going to be able to make the turn quite as quickly as the lighter vehicle is. And so the heavier object ends up bending less in the magnetic field. The lighter object is able to bend more. And we see 2 things. First of all, we see that there are 2 different masses that are present. The other thing that we see is that this photographic plate shows that the 20 AMU spot is much, much larger than the 22 AMU spot, which means that there's way more at 20 AMUs than at 22. Now, this is the kind of information that we're ultimately going to use to help us to draw some extra information out of the periodic table. So, first of all, the positive rate analyzer tells us that multiple isotopes exist for neon. That's our experimental evidence that we do have different isotopes. By definition, an isotope has the same atomic number, so the same number of protons, but different mass number, different number of neutrons. It is the proton number that is ultimately going to tell us what an atom is. So If I look at my periodic table, I can see that gallium, Ga, with its atomic number 31, is going to have 31 protons in that nucleus. Now, within a sample of gallium, I might find samples of gallium-69, which would have 31 protons and 38 neutrons, and a sample of gallium-70, which would have 31 protons and 39 neutrons. They're both gallium. They both react really similarly to each other. In fact, if I had two samples of gallium-138 or 169 and 170, I would have a hard time telling them apart from each other in appearance. I'd have a hard time telling them apart from each other in reactivity. Where would their differences manifest each other? In their abundance. One of them is more abundant than the others, and based on the mass of the periodic table, that average mass that is shown is a lot closer to 70 than it is to 69. I would expect to find more gallium-70 than I would gallium-69. But in terms of physical, chemical factors, isotopes rarely have any differences from each other in those regards. They usually show up in terms of their abundance and their radioactivity. The ones that tend to be the most abundant tend to be the most stable. The ones that are the least abundant tend to be the least stable and the most radioactive. You should have seen this in the post-lecture. I did talk about it slightly before. This is our common symbology, AXZ notation for symbols of elements and isotopes. Again, the mass number A here represents the total number of nucleons, total number of protons and neutrons together. The atomic number Z here represents just the number of protons. This is ultimately what determines what our element is. And we can represent that further by looking at X, which is our elemental symbol. So let's do a little practice. It's a little bit of review from what you saw last night. Write some symbols using that format for two different nuclides. One that has 6 protons and 7 neutrons, and one that has 95 protons and 146 neutrons. So take just a couple of minutes and go ahead and try to sketch those out. We have 6 protons and 7 neutrons. So the mass number of this would be 13. 6 plus 7 is 13. Atomic number would be 6 because there are 6 protons. I go to my periodic table. Periodic table says element number 6 is C, carbon. In the second problem, I have 95 protons and 146 neutrons. That 95 protons is my bottom number. I can also use it to identify. Element number 95 is AM, americium. Not on your element list, but a very common element in most of your homes. You have a smoke detector, you have americium in your home. It is the material that provides the electrical power for your circuitry that reacts to the smoke, and when smoke gets in there and breaks the circuit, allows the alarm to sound. Its half-life is the reason why you have to replace your smoke detector every so often, because once the americium runs out, it's no longer useful and no longer does its job. For the mass number, I need to add 195 and 146. That would give me 241. So far, not too bad. Any questions? All right. Let's go about trying to complete this table. I'll give you another couple of minutes. In the first box, go ahead and put the symbol. If there is a disparity between your protons and neutrons, so let's just do this first one together. If there's a disparity between the protons and the electrons, rather, that would be represented as a charge. And remember, charges go into the top right corner of that symbol. So in this case, 21 protons means an atomic number of 21. 21 plus 24 is 45, so that's my mass number. Charge is equal to protons minus electrons. So 21 minus 18 is a positive 3. So my symbol is going to look like this. Mass number of 45, atomic number 21. That is scandium as my element, and positive 3 as my charge. Go ahead and try to do the next two. So for number 2, we're given the atomic number and the mass number. So 89 and 39 are the numbers. Element number 39 on my periodic table is Y, yttrium. Now, I'm not giving any information about the electrons. Technically, I guess I could put anything I wanted in there within reason. For the sake of argument, let's just keep it neutral. So I would have 39 protons, 39 electrons if it's going to be neutral, and the number of, 39 electrons if it's going to be neutral, and 50 neutrons. 39 plus 50 gives me that 80, 89. Number 3, we can do kind of the same thing. 15 electrons, let's just assume neutrality. That would mean 15 protons, which would mean an atomic number of 15 and a mass number of 31. I put that into my symbol, 31, 15, and element number 15 is P for phosphorus. Okay, so let's move into average atomic mass then. We've talked about this a little bit. I mentioned the example with gallium and how gallium can have different values for its mass number, which means it would have different values for its atomic mass. Now, the numbers that are reported on the periodic table are average atomic masses. And how we calculate those average atomic masses is by using a weighted average. The weighted average takes into consideration two factors: the natural abundance of the isotope and its mass in AMUs. Now, if you've ever calculated a weighted average, its calculation is not too terribly difficult. In fact, your grade in this class is calculated in a very similar manner, where I take each subsection of the course, proficiencies, quizzes, exams, homework, post-lectures, and I multiply them by a given weight based upon the level of importance to the course. Exams are the most important, they have the largest weight. Homework is important, post-lectures are important, they're all given assigned weights. Now the natural abundance is just a percentage. How much of a given isotope is present on planet Earth at any one given time. And it's always relative to the other substances. So to answer a question like this, what I need to do is I need to do a calculation of the weighted average. Now, there are a number of ways to go about doing this calculation. I favor a method that, for me, seems the simplest. And that method is, if I have a percent abundance, understand that percent means parts of 100. And so these values are inflated to 100%, to 100 parts of a substance. Easiest way to get around it, though, honestly, multiply. If I multiply an atomic mass by its percent abundance to the correct number of significant figures for each one, and then add those three numbers together, I will get a value, an inflated value of the mass. And the reason I'll know it's inflated is when we do this, it'll make sense. The number is going to be really large. So the steps are simple. 1, multiply percent and AMU. 2, add the products together. 3, divide by 100 to get rid of the percents. So if I follow those steps here, 19.9924 multiplied by 90.4838 to 6 significant figures gives me 1,808.99 AMUs. $20.9940 multiplied by 0.2696 gives me to 4 significant figures this time, 5.660 AMUs. 21.9914 multiplied by 9.2465, this time to 5 significant figures, gives me 203.34 AMUs. Now, why did I round each one of those off? Because they were separate functions. If I were going to multiply all these together in the end, I wouldn't round until I was done with all the multiplications. But here, since I have to multiply and then add, I've got to keep my uncertainties in check. So I've got to round each multiplication off because it's going to be combined by addition in the next step. And that's why this had 6 sig figs, that's why this one had 4 sig figs, that's why this one had 5. They were all limited by the number of significant figures in that percent abundance. Now I add them together, 1808.99 plus 5.660 plus 203.34. I get 2017.96 AMUs. Now, when you do it this way, and you come up with this as your final answer, immediately your mind has to go to, well, that's way too high. There's no number over 280 on the periodic table for atomic mass. That's where that last step comes in. I divide it by 100. The actual atomic mass is 2017.96 divided by 100, which would be 20.1796 AMUs. And if I compare that value to the value on the periodic table, the one I gave you says 20.18. The one over here says 20.1798. We're in the right hash marks. So this is how you go about calculating weighted averages for percent by mass abundances. Now, if you're not given percent by mass abundances, if you're given fractional abundances, 0.904838, 0.002696, 0.092465, where all these numbers have already been divided by 100, the process is exactly the same. You just skip step 3, because that part's already been done. Coincidentally, you could do that first step up here. You could convert the percentages all to fractions on your own and divide by 100 individually. I just prefer to do it here at the end because that means I only have to divide by 100 once instead of each time for each isotope. That's a personal preference thing.